We have seen that there are two problems with user level threads. So one problem is, let's say problems or disadvantages. Okay, problems. There are two problems with this user level threads. So what are the problems? Blocking system calls. So what is blocking system call? If you make a call, let us say if you want a hard disk, and if the hard disk is currently being used by someone else, then you have to be blocked until that hard disk is going to be available. So in order to access the hard disk, you are going to make a system call, and therefore that particular system call is going to block you, right? So a process will be blocked because of the system call in case if the service that you requested is not available. Once it gets available, you will be unblocked, right? So blocking system calls in case of user level threads will block the whole task. So what is the meaning of this? Let us say we have a task, and in this task let us assume that we have many threads going on. Now even if one thread asks for a system call, if this leads to blocking, right, actually only this thread has to be blocked, but what happens is the entire task will get blocked. That is the problem with this. Now because of which you can clearly see that even though the other threads have no problem, they also are going to suffer because of this particular block, right? That is the disadvantage of user level thread. That is one disadvantage. And the other disadvantage is unfair scheduling. So let us say there is a task which is having 100 threads, and there is one more task which is having only one thread. Now if you use user level threads, our operating system will not know how many threads are executing in your process. For the operating system, it is just a process and it is just another process, right? So it will give 1 millisecond for this process, and I'm just assuming it, okay? In case if you are using a time quantum of 1 millisecond in round robin, then this process will get 1 millisecond and the other process will also get 1 millisecond, right? But the fair thing to do would be giving 100 milliseconds for this and 1 millisecond for this. That is the fair thing to do. But then without knowing it, our operating system will just give 1 millisecond for this and 1 millisecond for this. Now this 1 milliseconds have to be shared between 100 threads. Then first time this one will get the chance, and again this one will get the chance, second time this one will get the chance, and again this one will get the chance, which means by the time each thread here gets a chance, this thread will be getting 100 times the chance to execute, right? Which means this thread will be getting 100 times faster and these will be slow, right? So in order to overcome from this disadvantage, the only solution is to let the kernel know that we are having threads, and to let the kernel know that it is only one thread which is getting blocked and you can schedule the other threads. So for this reason we are going to use the solution called as kernel level threads. So in kernel level threads, what happens is whenever a process, generally the task, whenever it starts, it is going to start with one thread, and whenever it wants to create the next thread, right, this thread has to make a system call, and this system call is used to create the next thread. Therefore, exactly like how we create a new process, a new thread will be created. Got it? A new thread will be created by whom? By the kernel, right? Therefore, kernel is actually involved in the thread creation, and so kernel knows what is the thread that is created, and so kernel knows how many threads are there in the task, right? So Now what happens is, assume that later at some point of time this particular thread makes a system call and then it gets blocked. Now even though this thread gets blocked, you are not going to block the entire task. You are going to block only this thread, and this one will be scheduled, right? Therefore, it is easy in this case to attain parallelism. We are letting know the kernel that we are having multiple threads. Got it? And so this problem has been fixed. What is the problem? Blocking system calls will block the whole task. Okay. But here, one blocking system call will block only single thread, not the whole task. And also the second problem can be solved. So what is the second problem? Unfair scheduling. Now if the kernel has created the threads, and if it knows that there are 100 threads in this task and only one thread in this task, then kernel will appropriately schedule the thread. Instead of scheduling the process, like in this case, it will schedule the threads, which means each thread will now get equal amount of time. For example, this one will get 1 millisecond, 1 millisecond, 1 millisecond, and this one will get 1 millisecond. Therefore, as a whole, a task which is having 100 threads will get 100 milliseconds, and this one will get 1 millisecond. Therefore, it is a fair scheduling, right? But then what is the disadvantage of this method? So what are the problems in kernel level threads? Problems in kernel level threads. So it is very clear that while creating a thread, we are actually involving a system call. Therefore, it is expensive compared to user level thread, isn't it? Expensive compared to user level thread, but then it is slightly lower expense, right? Its expense is slightly lower compared to the creation of the process. So if you see a creation of the process, when you are trying to create a new process, let us say this is one process, and if you are trying to create a new process, you have to actually create everything, right? Therefore it is more expensive. But if you are trying to create a new thread, you are not actually creating everything, you are just sharing most of the things. Therefore if you look at the expense, creating processes is more expensive compared to creating kernel level threads, and creating kernel level threads is more expensive compared to creating user level threads, because user level threads are created by the user library without any system calls. Both of these are going to get system calls, but this is a heavyweight process, it is a lightweight process, therefore the cost is less here compared to this. Got it? So expensive compared to user level threads for creation, isn't it? And what is the second problem? The second problem is switching is not done without a system call. So switching a thread here requires context switch, right? So switching a thread, kernel level thread, requires system call again, right? Now what happens is, just like the switching the processes, when we switch the thread, you have to call the operating system. So operating system call has to be required, system call has to be required. Then what happens is, your kernel will get into the picture and it will try to change the context. But anyway, the context switching is very simple, because only registers have to be changed, everything is similar, right? So anyway, again, switching is also expensive compared to user level threads, but comparatively less expensive, when you compare it with the process switching, right? So both the approaches, user level threads as well as kernel level threads, are having some disadvantages, but they are better compared to using multi-programming or more processes for doing the same task, right? See, overall threads are performing well compared to the process. If you have to do only one particular task, like web server, right? But then the problem with the threads is, there are certain problems like this, right? And both the types of threads, either the kernel level threads or user level threads, are having these problems, and so many some of the operating systems, they go with a hybrid threads, which means they are combining the concepts of kernel level thread and the user level thread, and they are calling it as the hybrid threads. We shall see about the hybrid threads example now. Okay, fine.